We now move on from momentum to momentum's cousin, energy. Energy is also going to be a conserved quantity, but while momentum is a vector, energy is a scalar and is thus a little easier to work with. In addition, energy is something that's talked about in the news and in our day-to-day lives. And in addition to the physical definition of energy and the conservation laws that come with it, I am going to spend this lecture going over some of the different sources of energy and the pros and cons of each for our modern way of life. We start out our exploration of energy with the concept of work, which is a similar concept to momentum, except instead of multiplying by time, force is multiplied by the distance over which it acts on force acts on an object. So work is equal to force times distance equals FD. So lifting a weight twice as high versus a constant mg takes twice as much work. The units of work are going to be the units of FD, which is force times distance. So mass times the units of acceleration, length per time squared, times length is equal to mass times length squared divided by time squared, or mass times length divided by time squared. So these might look familiar to you because they are also the units of m times speed squared. And we have Einstein's famous equation that you might not know what it means, but you probably know what it is. E equals mc squared. Energy is equal to mass times the speed of light squared. So units of work are also going to be the units of energy, giving us a clue to the eventual development of a theory of energy. Energy is the unit which is transferred when work is done on or by an object. The SI unit is alternatively called kilogram meter squared per second squared, Newton meters, or joules. Other units include the calorie, the big C calorie, and electron volts. Work generally falls into two categories. One of these is the work done against another force. When an archer stretches her bowstring, she is doing work against the elastic forces on the bow. Similarly, when the ram of a pile driver is raised, work is required to raise the ram against the force of gravity. When you do push-ups, you do work against your own weight. You do work on something when you force it to move against the influence of an opposing force, often friction. The other category of work is work done to change the speed of an object. This kind of work is done in bringing an automobile up to speed or in slowing it down. Another example of this kind of work is when a club hits a stationary golf ball and gets it moving. In both categories, working against a force or changing speed, work involves a transfer of energy. So before we talk about energy in general, we want to talk about power, which is the work done divided by a time interval, or dW dt. So a way to think about it is that a liter of fuel can do a certain amount of work, but the power produced when we burn the fuel can be any amount depending on how fast it is burned. It can operate a lawnmower for a half hour or a jet engine for a half second. And this is the difference between the two powers of the two different types of engines, where while they have the same work done, there are different powers, and higher power means that the work is done over a shorter time interval. So the unit of power is joules per second, or watts for SI units, or horsepower for imperial, which is again the units that England and the US tend to use. So 1 horsepower is equal to 746 watts. Working backwards, you will also see that instead of using joules, when you get your energy bill, a lot of the time it's the energy that you use is measured in units of kilowatts hours, which is a kilowatt or 1,000 watts times 3,600 seconds or an hour. Kinetic energy is going to be the first use of the term energy that we're formally going to use. It used to be called the oomph of an object and is a measurement of how fast an object is moving. So the work kinetic energy theorem states that the work done on an object by the net force acting on the object is equal to the change in kinetic energy. So kinetic energy equals 1/2 mass times speed squared, or 1/2 mv squared. Potential energy is our other type of mechanical energy that we're going to be talking about, which is equal to the potential for movement caused by a force. It can be calculated as the work needed to move against the force to get to a certain position. The amount of gravitational potential energy possessed by an elevated object is equal to the work done against gravity in lifting it. The work done is equal to the force required to move upward times the vertical distance it moves. Remember that work is equal to F times d. The upward force required while moving at constant velocity is equal to the weight, mg, of the object. So the work done in lifting it through height h is the product mbh. A useful property of gravitational potential energy is that it does not depend on the path to get there. If you just lift it straight up as you do in the first diagram here, then it will have the same potential energy as if you roll it up a ramp 5 meters, or if you climb it up a stair, one stair at a time for a height of 3 meters, which is the same height that you were just initially lifting it up and the same height that the ramp comes to. So because all of these are at the same height, they have gained the same amount of potential energy. Another facet of this is that if you go down in any of these directions, going straight down, going down the ramp, or going down the steps, then you are going to lose the same amount of potential energy. And as we will see later, this means that you will gain the same amount of kinetic energy no matter what. So going more into that, we have conservation of energy. Energy cannot be created or destroyed. It may be transformed from one form to another, but the total amount of energy never changes. So the change in kinetic energy is equal to the work done on the object, which is opposite to the change in potential energy, since that was defined as the work which was needed to be done against the force in order to lift it to a certain point. Another consequence of this is that energy allows us to find the final velocity without worrying about paths. For all the paths that you see on this image, 1, 2, 3, and 4, a metal ball is going to be going along different paths in order to reach a final destination, which is at the starting at the same height and ending at same different height. Depending on the path, you are going to see the object arrive at its destination in differing times. As path 1 has a steeper acceleration initially and has you get to a final velocity first, it is going to be the first one to hit the wall at the back. And then path 2 and path 3 and path 4 are going to increasingly take longer to get there because they have their acceleration later. However, what does happen is that since there is a change in potential energy, which is the same for all of them, because they go from the same height to the same second height, the final kinetic energy is going to be the same for all of them, and all of them are going to have the same final velocity. With this in mind, we get to an ideal that is going to be very useful for the development of human history, which is the ideal of a machine, where the work input is equal to the work output, but the force output can be different depending on the distance that you travel. On the right, we have a lever where we exert a small amount of force over a great amount of distance, and by positioning the lever so that the distance on the other side of the lever is going to be smaller, it is going to create a greater amount of force because the work that you put in is going to be equal to the work that goes out by conservation of energy. This is, of course, ideally. Even basic levers have a little bit of energy loss to friction or heat and are only about 98% efficient. But ideally, the work input should be equal to the work output. And using more complicated systems of machines such as pulleys, we are able to get forces which will have a greater output than the input that we put in. The efficiency of a machine is the useful energy output divided by the total energy output. In the diagram at the top, you have a weight which is hanging above a piston kind of, where the weight has potential energy, and as the weight is dropped, it drops on top of a gas which is compressed to cause more heat and more molecular motion. And then the kinetic energy is completely lost as it comes to a standstill, but there is more heat. The book says that the graveyard of mechanical energy is thermal energy because the work that would otherwise be done to do useful work is instead converted into the motion of molecules, which is a change in kinetic energy for the molecules, but isn't very useful. It just heats up the gas or the material or whatever you're looking at. Finally, we're getting to different ways to use and transfer energy. So the sun is the source of almost all of our energy. Energy is bottled sunlight. So plants photosynthesize to create energy efficiently, and then this energy is transferred up the food chain. Fossil fuels are leftover energy from organic matter, many steps removed from the sun. We can also directly harvest solar energy with photovoltaic cells, and even the wind is due to temperature differences in the air caused by the sun. The first type of energy that we're going to go over is going to be photovoltaic cells because these are going to be the energy that is directly taken from the sun. They use Einstein's photoelectric effect to take sunlight and convert it directly into electric energy, as we are going to talk about much later in the class. And they are about 47.6% effective at best as of 2024, but the sun puts out a lot of light. So although they are not the most efficient methods of transferring or storing energy, there is so much sunlight that it almost makes up for it. However, they are not able to be used at night and must be supplemented with other forms of energy or have excess energy stored. They used to be expensive to manufacture, but are getting steadily cheaper and account for a little less than 25% of our energy. Wind power converts the kinetic energy of wind pushing along a turbine, which is just a big fan blade that is moved and converts mechanical energy into electrical energy. It is very old technology used in windmills in Persia for as far back as the 9th century and supplies about 2% of the world's electricity. The theoretical max efficiency is 59%, but practically it's about 50%, which is around the same as photovoltaic cells. However, it depends heavily on location, and many ideal wind sites are in remote locations, and the energy would have to be transferred from that location to a city or to a more populous area. Hydropower also uses the kinetic energy of high lakes and rivers to drive turbines, as the potential energy is converted into mechanical kinetic energy. It drives through a turbine, and the turbine converts the energy into electricity. They are the modern version of water mills, which were invented at the latest in the 3rd century BCE and are about 90% effective. So they are definitely the most effective technology that we've talked about so far. However, there is the problem that we need to drink water and use water for other things, and that water is getting significantly more scarce as time goes by. While water is technically a renewable resource because of the water cycle, which brings used water back into the atmosphere and rains it down onto the land again, it is still a finite resource and must be carefully controlled alongside other resources, unlike the power of the sun that we are seeing in photovoltaic cells. As an aside, I want to talk briefly about gravity batteries, which are a way of storing energy rather than producing it. A normal battery converts chemical potential energy into electrical or kinetic potential energy of electrons. A gravity battery lifts the water up and converts the energy into gravitational potential energy, which can then be converted back into kinetic energy using turbines. It works kind of like a dam in the same way that we were talking about just now, but it is a way of storing energy rather than producing it. Geothermal power uses the heat of the earth as a form of energy, which is then converted to kinetic energy using dry steam power stations, flash steam power stations, and binary cycle power stations. It has greenhouse gas emissions of about 5% of coal-fired plants for the same amount of energy, but it is disruptive to land stability, geyser cycles, and releases trace amounts of toxic elements. It's also only around 7 through 10% efficiency, so a lot of the energy that is released by the steam, which drives turbines, is only going to be released into the atmosphere instead of driving the turbines and allowing us to use it as useful electric energy. Natural gas and other fossil fuels are non-renewable, meaning there are limited stores of it available, which will eventually be depleted. Energy is released via burning, which releases greenhouse gases and pollutants, and there is only an average efficiency of about 35% for coal, 45% for natural gas, and 38% for oil fire. The greenhouse gas emissions from fossil fuels include CO2 emissions, which have been increasingly getting bigger since the dawn of the Industrial Revolution, and which are driving climate change. This graph is part of a larger graph on the website XKCD run by Randall Munroe, who was an ex-NASA physicist. I recommend that you go through the larger graph because it gives you a really good scale about the types of changes we've seen in the past versus the changes that we are currently seeing with greenhouse gas emissions. The final energy that I want to talk about is nuclear power, which uses energy released from nuclear decay to heat water and the steam from the heated water to power a turbine. It is cost-effective after initial construction costs and has low pollution, but has a limited supply of about 80 years for our current stockpile, which is still a lot more than we have for fossil fuels. Waste management is a problem, as is the safety of older plant types without proper maintenance. As we have seen in Chernobyl, Fukushima, and 3 Mile Island, if these plants are not properly maintained, then they can cause massive environmental damage and provide a huge danger to the public. Another problem is that because uranium has to be mined, it has a lot of the same ethical problems as coal mining does. A lot of the early mining was done by Native Americans who didn't speak English and weren't properly warned about the dangers of radiation. When they inevitably got cancer, it was blamed on the fact that many of them were smokers, and the government was able to get out of culpability for the dangerous mining that they had been put through. That said, there aren't any perfect energy sources out there, and we have to be aware of the dangers and the potentials of these energy sources if we want to make an informed decision.